Hello, and welcome to the Scientific Adventures of Beardman. Today we're looking at the California Science Test, known as the CAST, and we'll be looking at questions 25 through 32 as we lead up to the performance tasks. So sit back, relax, and put on your thinking cap.
Let's go ahead and begin with question 25. A student drops a tennis ball from the top of a building as shown in the picture. Air resistance is negligible. Explain how the student can determine the height of the building if the kinetic energy of the ball is known when it hits the ground. In your explanation, use the terms kinetic energy, gravitational potential energy, acceleration due to gravity, mass, and height. Do not use equations. Enter your answer in the box provided. Go ahead and type up your answer now. All right, so there are two main things you need to make sure that you included in your answer here. The first is the idea that the kinetic energy at the bottom is equal to the gravitational potential energy at the top, because we have conservation of energy going on here where we start off with gravitational potential energy. There's no air resistance. Air resistance is negligible. So that means that all the mechanical energy we have at the beginning we'll still have just before it hits the ground. But at the top, it'll be gravitational potential energy, and at the bottom, it'll be kinetic energy. I just realized my arrow looks like this is kinetic energy. This is the gravitational potential energy there. But those have to be equal. So if we know the kinetic energy at the bottom, then we also know the gravitational potential energy at the top. Now we know, the second thing you need to know is that the gravitational potential energy is equal to mass times the acceleration due to gravity times the height. So if we're trying to find the height, we're going to have to divide both sides by mg. Okay, and that cancels out over here. And we see that the height is equal to the gravitational potential energy divided by the mass and divided by the acceleration due to gravity. Now, I did this in terms of equations, but you can just say the things in sentences that I just said. The kinetic energy at the bottom must be equal to the gravitational potential energy at the top because energy is conserved. Then a second sentence would talk about how to find the height. You'd need to take the gravitational potential energy and divide by the mass and the acceleration due to gravity. Notice that all of those things were the terms that you needed to include in your statement. All right, moving along to question number 26. Results from a wide range of climate models simulations suggest that Earth's average surface temperature could be between 1.1 and 5.4 degrees Celsius warmer in 2100 than it was in 2015. Some species, such as sugar maple trees, are adapted to survive cooler temperatures and have historically occupied northern parts of North America. Scientists claim that rising average temperatures will change the distribution of sugar maple trees in North America. In addition to global surface temperature data, which data, if collected, would best support or refute the claim? A. The soil temperatures should be measured daily for 1 year at 2 separate locations. B. Core samples of the largest sugar maple trees should be taken to determine how old the trees are. C. The total number of acres of forested land throughout the range of sugar maple trees should be recorded annually. D. Sample sites should be set up throughout the range of sugar maple trees and the number of sugar maple trees counted every 5 years. Go ahead and mark your answer now. So to answer this question, we've got to take a look at what's going on here. We have a claim. We have two parts of that claim, right? We have the independent variable the thing that's causing the change, and then the dependent variable, the distribution of sugar maple trees in North America. Okay, we're told that we already have the data for average temperatures. So that means we need data to support or to figure out what's happening to our dependent variable, the distribution of sugar maple trees. And so we need to look for something that's going to help us to know the distribution of the sugar maple trees, how they're distributed. So we can see here that we can see here that the soil temperature, that's not going to tell us the distribution of the trees. The core samples, to see how old they are, that's not going to tell us the distribution of the trees. The number of acres, it's kind of getting towards distribution, but it's still not, still not where they are. It's just the total number. And here we see in D, sample sites should be set up throughout the range and the number of sugar maple trees counted every 5 years. That way we would know how many trees are in different places and if they're being distributed differently. So D would be your best answer. Let's go ahead and move on to question number 27. The moon is thought to have formed shortly after the formation of Earth, and therefore the age of the moon is comparable to that of Earth. The surface of the moon is covered by ancient craters formed by impacts of small solar system objects such as meteoroids, but the surface of Earth shows no such craters. Which two statements are valid explanations for this observation? The moon shielded Earth from impacts in the early solar system. Solar system objects are more likely to impact satellites than planets. Geologic activity on Earth's surface has destroyed evidence of impacts. The moon has a very thin atmosphere, eliminating erosion due to weather. Earth's atmosphere protected it from impacts by large solar system objects. So go ahead and choose the two statements that are valid for this observation. All right, so let's take a look at these one at a time and talk about why they make sense or not. So first, the moon shielded Earth from impacts in the early solar system. Well, to shield it, I think the idea is that they're picturing like people thinking of the Earth here and the moon goes around the Earth. So because it's like in all these places, it could shield it. But at any one moment, the moon's only in one place and it's a lot smaller than the Earth. So the Earth has a much bigger gravitational field. The other thing they might be thinking might confuse people with this one is Jupiter does to some extent protect the inner solar system because of its large size. Anything that's closer to it because of its great size can get pulled in and end up landing on Jupiter, so it can't get all the way into the Earth. But anything coming from somewhere else would still get there. Solar system objects are more likely to impact satellites than planets. There's no reasoning for here, so neither of these would be I wouldn't consider it a valid explanation. And they're not more likely to hit satellites. Satellite has less gravitational pull because they're smaller, and so they're less likely to be hit than planets, which are bigger and have a greater gravitational pull. Geologic activity on Earth's surface has destroyed evidence of impact. Yes, plate tectonics, definitely land gets destroyed as it gets submerged under other land. And so that is definitely a reason why evidence of impacts would be diminished. Also, the formation of mountains would rise the land up and crunch it together, and you would no longer see a crater. So that is a good one. I like that. So let's go ahead and click that one. So the next one, the moon has a very thin atmosphere, eliminating erosion due to weather. Yes, because there's no wind or rain or anything else, because of that thin atmosphere, that would eliminate erosion, and therefore the craters would stay for a long time on the moon, whereas on the Earth, with a thicker atmosphere and with weather, that would cause erosion of features like craters. Earth's atmosphere protected it from impacts by large solar system objects. I do like the idea that Earth's atmosphere protects it, but it's really protecting it from smaller things. Larger things don't have enough time to burn up on their way through. But even more than that, this question, the statement we're trying to find an explanation of, is that craters formed by impacts of small solar system objects. So, what happens to large solar system objects isn't pertinent, and therefore we can eliminate that choice. All right, moving on to question number 28. A student is planning an investigation to compare the strengths of the forces of attraction between the particles in the following solid substances: sulfur, S8, iodine, I2, sodium chloride, NaCl, and tin, Sn. Which statement includes the best plan for the students to follow and the correct explanation? Measure the density of each of the substances. The denser the substance, the stronger the forces of attraction are between the particles of that substance. Measure the melting point of each of the substances. The higher the melting point, the stronger the forces of attraction are between the particles of the substance. C. Measure the electrical conductivity of each of the substances. The higher the conductivity, the stronger the forces of attraction are between the particles of the substance. Sorry about that. D. Measure the solubility of each of the substances in water. The less soluble the substance, the stronger the forces of attraction are between the particles of the substance. Go ahead and pause the video and mark your answer now. All right, so as we take a look at that, we're asked about how these particles, how strongly they are attached to each other. Well, in a solid, the particles are bonded to each other, okay? And that makes them so they can't move around. So what we're really asking is, how do we take this particle and break the bond that's holding it to the molecule next to it? Well, what that looks like when we break the bonds between them and they're no longer held in place, we're taking a solid and we're turning it into a liquid. Okay, and that's what happens when you melt a substance. So B would be the correct answer here. Let's really quickly go through the other ones and take a look at what's going on there. Density. Density would primarily be how many protons and neutrons are in the nuclei of the atom, but also how close the atoms or particles can be stacked to each other, depending on the formation, like the crystalline structure of the molecules. That could affect the density also, but largely how many protons and neutrons are in each nucleus. So that's not about the strength between the things. But I like the idea, hey, if it's stronger, it'll pull them closer. Not necessarily, and there's bigger factors for the density. Electrical conductivity it has to do with how well the electrons can move from one atom to another. That's not really about the force between particles. It's more about the force within the atom. Can some electrons leave? And finally, solubility. Solubility is another great idea because solubility is breaking these atoms apart, but there's other particles from the solvent that are getting in there to help make it happen. All right, let's go and move on to question 29. Scientists have developed a computer simulation to model changes in water quality due to human population growth and land use. The outcome of the simulation is a predicted profile of diatom diversity. Diatoms are unicellular photosynthetic algae. Diatoms can be used as indicators of water quality because of their diversity and abundance in unpolluted water. A town that is next to a river is planning to build a new housing development of 100 homes along the river. Scientists sampled water downstream of the town during the summer and produced a baseline profile of the size and diversity of the diatom population in the water. Those data were entered into the simulation. In order to model the effect of adding 100 homes, select a checkbox in each row to indicate which of the parameters should be kept the same or which or changed in the simulation. So you're either going to mark change parameter or keep parameter constant for humans population size, sampling season, sampling site, or number of samples. Go ahead and pause the video and think about your choices and make them now. Since we're looking at an experiment here, that means we're going to have two variables, the independent variable and the dependent variable. Our independent variable is the thing that we're changing. We're looking at adding 100 homes. And the dependent variable is the thing we're testing, which is the amount of diatoms, okay? So the amount of diatoms, the diversity and abundance in unpolluted water. None of these choices talk about the number of diatoms, so therefore these things will all have to be held constant. None of them will be the thing we're changing for the diatoms. Okay, but for adding the 100 homes, the human population size is the thing that we are changing. So that one you're going to want to change. We're going to change it to 100 extra homes, however many people that represents. And we're going to want to keep the sampling size, sampling site, and the number of samples the same so that we know that any changes are caused by the 100 homes. All right, let's move on to question number 29. Question number 30. A block with a mass of m is sliding to the right with a velocity of v on a horizontal frictionless surface. It has a head-on collision with a larger block with a mass of 9m that is initially at rest. After the collision, the blocks are stuck together and move to the right along the same path with a velocity of 0.1 v. Which two statements are correct about the forces exerted on the blocks during the collision? All forces exerted on both blocks sum to zero. The net force exerted on the block with a mass of m is zero. The net force exerted on the block with a mass of 9m is zero. All external forces exerted on the two-block system sum to zero. Go ahead and pause and record your answer. All right, so when two blocks hit, we've got a block M that's moving, and we've got a block 9M that's stationary that gets hit. So when this block hits the other one, we have contact here, which will give us a Newton's third law pair of forces. The 9m block will push on the m block, and the m block will push on the 9m block as part of a single interaction. And so the molecules in the 9m block will be too close to the molecules in the m block, and so they will repel each other. Their nuclei will repel each other, which causes equal forces because they don't know anything else. They're just repelling each other, just like magnets, more or less. And so that's going to cause equal and opposite forces. And so therefore, all forces exerted on the blocks sum to zero because there's only two forces, the m pushing on the 9m and the 9m pushing on the m. And so if those are equal and opposite, then all the forces sum to zero. The net force exerted on a block with mass is zero, of m is zero. Nope, that block is going to slow down a little bit. The net force exerted on the block with a mass of 9m is zero. That one's going to speed up a little bit, so it definitely will have a net force. All external forces exerted on the two-block system sum to zero. Yes, because the only forces there are these two forces right here that we said are equal and opposite, and so they will sum to zero.
All right, now let's move on to number 31. A bathtub model, like the one shown, can explain the flow of carbon through Earth's systems. Carbon sources contribute to an increase in atmospheric carbon by releasing carbon dioxide. Carbon sinks contribute to a decrease in atmospheric carbon by storing carbon for long periods of time. And here we see the bathtub model of carbon flow. We have sources of carbon, which is the faucet. Right now, size of faucet is much larger than drain, and sinks of carbon equal the drain. Select a checkbox in each row to sort the carbon sources and carbon sinks. We see the two columns are labeled faucet source and drain sink, and we have 5 things we have to sort: burning fossil fuels, deforestation, ocean absorption, volcanic eruptions, converting farmland to forests. Go ahead and pause the video and make your selection now. Selections. At these one at a time. We got to remember that faucet or source is things that will take carbon from being stored somewhere and return it to the atmosphere as carbon dioxide or methane. And the sink will be stuff that takes stuff out of the atmosphere and puts it into something made of carbon. So burning fossil fuels are made of carbon largely. And so when they burn, they release that as CO2 and put it into the atmosphere. That's things like gas, oil, coal, natural gas. Deforestation, the trees are a store of carbon. And so if we get rid of those trees as they decompose, they're going to release that carbon back into the air. And they won't be drawing carbon dioxide out of the air. So both increase the amount of carbon dioxide in the air. Ocean absorption, if the oceans are absorbing carbon dioxide, that is one place it goes. Of course, that has its own problem with coral reefs and such. But moving on, as far as this is, it's a place the carbon dioxide can go other than the air. Volcanic eruptions, that takes carbon that's been trapped in the rocks and releases those gases into the air when it erupts. And then finally, converting farmlands to forest. Farmland producing crops that get eaten and then consumed returns the carbon dioxide back into the air, whereas forests, it will store in the trunks and limbs of that forest for a long time. So that is a sink. Forests will take it out of the air and put it into the wood. That's how they grow. All right, moving on to number 32. Scientists studied a population of snowshoe hares and their predators, Canadian lynx, in an ecosystem. The graph shows how the population sizes of lynx and snowshoe hares changed between 1855 and 1925. And you can see the graph here with the red representing the populations of the snowshoe hare and the blue representing the populations of the lynx. Complete the sentences using the lists to explain the relationship between the two species. When the hare population increases or decreases, the lynx population increases or decreases. This is an example of a density-dependent or density-independent factor resulting in cyclical changes. Go ahead and pause the video and make your selections now. So to start answering this question, let's take a look at the last one here, density dependent and density independent. And that has to do whether the factors that affect the population are dependent on how dense that is or not. Things that are independent tend to be things like wildfires or a volcano erupting, or things that it doesn't matter how much of the thing there is. But this seems to follow definitely a cyclic pattern, meaning we have high amounts and then low amounts, then high amounts, then low amounts, then high amounts, then low amounts, and so forth, cycling over the years. So I think it's pretty clear it's going to be a density dependent. And we can see more or less that when the red gets higher, the blue gets higher. So we could say that as the hare population increases, that makes the lynx population increase. Why do we say it that way? Well, you can see usually the red peak precedes the blue peak. Okay, presumably because if there's more food, then there are more lynxes that will live to eat that food. They'll be well fed, and so they'll reproduce and so forth. And then once you get enough lynxes, then they eat up all the hare population, and they end up both plummeting. And so we get this kind of cyclical change. Now, an interesting thing here is, yes, when the hares increase, the lynxes increase, but notice when the hares decrease, that also means that these decrease. So it's a linear relationship, directly proportional, however you want to say that. But either of these answers would be acceptable. Increases, density dependent, or decreases, density dependent. Brings to an end our analysis of questions 25 through 32. I hope you enjoyed learning with us. If you did, click the like and subscribe button there and join us for the next section, 33 through 38, as we look at the biology performance task.